Hello everyone, this is Torben Schulze speaking on behalf of our team at the company IAV, presenting our article called Comparison of Switching Power Losses of Fixed Frequency PWM, Hysteresis Control and Delta Sigma PWM. As it is widely known, the traction drive of an electric vehicle consists of a battery, an electric machine and an inverter, all of which exhibit a certain efficiency with which they utilize their provided energy. And it is precisely these efficiencies that are crucial to the vehicle's range. In our article, we focus on the loss characteristics on the inverter, and I'm going to preempt the paper's punchline here by saying that we demonstrate analytically and numerically how inverter switching losses can be reduced by up to a factor of 1/3. The core reasoning followed in our paper is deduced from the fact that the switching power losses will be directly affected by the phase current at the switching points. This is illustrated in the following figure that shows a variable switching frequency together with a phase current over time for one phase system. If we now deliberately shift the switching events so that we switch a lot at low current and only seldomly at high current values, the switching power losses will be reduced, whereas the average switching frequency remains the same. In our paper, we now analyze how efficiently we can decrease these switching losses. We examine this effect for one-phase systems, as it allows us to elegantly derive expressions for the efficiency by purely analytical means, and for three-phase systems, as these represent the topologies that are commonly used in modern electric vehicles. In our paper, in order to quantify the efficiency of our switching strategy, we compare the losses of three different PWM patterns with each other. First, there's a sine triangle PWM, shown here above, which is operated using a voltage forward control. As it is a fixed frequency PWM, it is not susceptible to our optimization approach and therefore serves as a kind of benchmark that we try to surpass. Second of all, there is the hysteresis control shown here in the middle, which is a direct current control scheme that through the hysteresis band gives a constant current ripple and that is going to be naturally accompanied by a variable switching frequency. Lastly, our analysis covers the Delta Sigma PWM shown here below, whose digital implementation already exists for driving electric machines. Its working principle is based on a Class D amplifier with a voltage feedback control. It also features a variable switching frequency, this time generated by a constant ripple of the integrated voltage error. All three PWM patterns drive a B2 inverter and a one-phase AC machine. Let's start with the one-phase systems. In what follows, we will derive analytic expressions where possible and complement these by numerical studies of important operating points. The starting point of our analysis concerns an analytic derivation of the instantaneous switching frequency for a hysteresis PWM and the Delta Sigma PWM to the analysis of the corresponding switching behavior. We do the analytics under the conditions of zero resistance and by neglecting dead times as well as noise failures. Returning to our figure, we see that despite the simplifications, the comparison between our analytically derived expression, here shown in orange, and a full simulation shown in blue, shows only marginal differences. Furthermore, we show that under the given conditions, hysteresis control and Delta Sigma PWM will actually produce exactly the same switching frequency and can thereby be seen as a kind of digital and analog counterparts to each other for this particular problem. The efficiency gain that we will later show will therefore be true for both of these PWM patterns. For the full derivation, please visit our article. Having derived the instantaneous switching frequency, we now possess the means to evaluate, again analytically, the ratio of switching power losses between variable switching frequency patterns and fixed frequency patterns. For this, we assume a linear dependence between the switching loss energy and the phase current at a given switching event, which allows to express the switching power losses purely through the absolute phase current and the instantaneous switching frequency. We then show that the ratio R of switching power losses, namely how much we win or lose with our approach, can be expressed by only using two variables, namely the average amplitude of the switching frequency F and the power factor cos phi. If we analyze the limits of this equation, it can be seen that it has a minimum at 66.66%, meaning a decrease of switching losses by a factor of 1/3. To show that this efficiency gain is not a wild boundary effect, but instead can be utilized at relevant operating ranges, we emphasize that the decrease is still 15% when the amplitude of the switching frequency equals half of the average switching frequency. In order to validate these analytically derived results, we cross-check them by numerical simulations at relevant operating ranges. As can be seen, again, analytics and numerics match quite well. The observed advantage is high at a power factor close to 1 and below a factor of 1 over square root of 2. The delta sigma PWM actually produces a disadvantage compared to fixed frequency PWM because here we switch preferably at high current values. The 100% break-even point can be calculated out of our previous equation and is pictured at the poster as a red line in the plot. Therefore, the operating points and the operating ranges will be decisive regarding the success of our shifting strategy. We now turn to three-phase systems. As the results for one phase have been indeed promising, your hopes might be high to find an equally nice situation for the three-phase counterpart. Yet, a close inspection of the three-phase systems will reveal a much more grim situation that translates into much lower efficiency gain. We provide here an intuitive explanation of how the inherent structural properties of three-phase systems are directly responsible for this unfortunate fact. As you remember, our whole approach is based upon the idea to shift switching events from high current values to low current values. In a three-phase systems, not all three phases can be simultaneously minimized, and shifting the switching events to low values in one phase will lead to the opposite effect in another phase, as shown in the plot below. If we once again rightfully assume a linear dependence between phase current on the one hand and switching loss energy on the other hand, the total three-phase switching power loss will be proportional to the so-called Manhattan norm of the three individual phase currents. Now, in contrast to one-phase systems, where the Manhattan current can drop all down to zero, the three-phase Manhattan current only drops down to about 7/8 of its maximum. Hence, already from this intuitive picture, we can anticipate that the fundamental effect will decrease by a factor of 8 compared to one-phase systems. This is indeed confirmed by our simulation results shown above, where for our analyzed operating points, the efficiency difference between a three-phase delta sigma PWM and a conventional space vector PWM does not exceed 2%. As the structural properties present a significant obstacle towards reducing switching power losses through the absolute phase current, we spend the remaining part of our article with a discussion of other approaches to reduce switching power losses. One obvious idea that comes to mind is simply to lower the switching frequency in order to reduce losses, yet for a fixed carrier frequency PWM, this will result in an increased current ripple that induces higher losses in the electric drive. Therefore, we examine a three-phase hysteresis approach with regard to the current trajectory and show how it can be used to minimize the switching frequency in a more elaborate fashion. The figure here shows a sketch of a typical current trajectory in the alpha-beta coordinate system using an algorithm that minimizes the switching frequency. What is now special in our approach is that the algorithm is again formulated using purely analytical expressions for the switching times. To its end, we use a predictive model that calculates at each switching point the current trajectories and thereby the time interval until the next switching takes place. And it does so for every available static voltage vector. For each switching event, we analytically derive all the relevant parameters such as current distances, switching intervals, and traversed angles. For the exact derivations, we again refer to our article. The results are then getting weighted with the switching costs, giving rise to a list of optimal switching vectors that can minimize the switching frequency for different points of operations. The maximum alpha-beta current ripple over time is hereby limited to a constant freely adjustable value, here highlighted by the black hysteresis band, providing a degree of freedom to optimize switching power losses in the electric drive. So, concluding, we have shown how a switching frequency shifting strategy can be utilized to considerably lower the losses that appear in an inverter. We have proven analytically and numerically that sensible operating points will feature a loss reduction of 15% with a theoretical limit of even 33%. We have further shown how the digital delta sigma PWM and the analog hysteresis control have a coinciding instantaneous switching frequency in one-phase systems. In the future, we will extend our analysis towards the impact of our switching frequencies to other important parameters, such as the total harmonic distortion. Our analysis of three-phase systems shows, unfortunately, that the effect is less pronounced here. Yet we have shown how other approaches such as hysteresis control will be able to reduce switching power loss with a lower average switching frequency without increasing ripple harmonics, and we think that a combination of both of these methods, hysteresis control on one hand and delta sigma PWM on the other hand, might be a direction worth investigating, which is what we are planning in the future. I hope you did like this brief presentation of our marvelous poster. Do not hesitate to contact us during the poster presentation or directly read our paper to achieve more insights. Until then, thank you for your attention and enjoy the PSYM 2020.